Okay, so we'll do a review of starting from analysis. So as I said, the main part of the exam will be focusing on the second part of the semester. So you can focus your review efforts on that. So I skipped requirements because I'm focusing on the second part of the semester. So analysis class is abstraction of one or several classes in the implementation. So in your implementation, you may have C++ classes, but that's not an analysis class. One analysis class may be turned into dozens or even hundreds of C++ classes. So it's very abstract. Focus on functional requirements only. Non-functional requirements are done at the design stage. For example, security, performance, reliability, all that shouldn't be a part of the analysis stage. Analysis only cares about functional. That is, can you register for a class? Can you assign a student to a course, etc. So analysis class is a conceptual. That is, attributes are conceptual. You can use any convenient type you want, not just programming language types. Behavior is defined by textual description. Relationships are conceptual. So you have three analysis classes. Boundary models the interaction. So you can have either icon-shaped boundary class, or you can have a regular class diagram notation with a single compartment with a name only, no attributes or operations, with a boundary stereotype. This is a stereotype. So it's models the interaction between the system and its actors. So could be a UI, user interface, if the user is a actor is a human user, or devices if the actor is some other system. So description is a high conceptual level. Describe what, not how. Encapsulates and isolates changes in the system's interface. That is, you can have, say, professor UI as a boundary class. Then you can design any UI you want. Any dialog design, you can change it later. But the professor UI is an abstract class that will be there. That's not changed during your design. So it's very just points to a boundary concept. Doesn't specify how the UI is actually done. So you can identify boundary classes from use case descriptions. So strategy is initially identify one boundary class for each actor use case pair. So here we say instance object because at this point it's different from domain model where we're dealing with classifiers. Here we say boundary class, but it's actually we're more interested in the runtime behavior, so we're more interested in the instance of the boundary class. Typically, one boundary class has one instance. Obviously, it's not an implementation instance. It's a conceptual instance. So human user represents primary UI, and external user represents communication interface. So later, you can aggregate them into other boundary objects. So here's the domain model for the professor courses. Here's the use case model. And here's the detailed specification. Now, professor has two use cases. Therefore, based on the strategy, you assign a boundary class for each use case actor use case pair. Therefore, you have select courses to teach UI. The convention is to append the UI to the end of the use case name as the boundary class name. And later, perhaps you can aggregate these two into a single boundary class with a composition relationship with the fine-grained boundary class. Or you can refine a single boundary class into a multiple, more fine-grained boundary classes. So, entity class is a long-lived model's long-lived information. So, gets its data from a database. Notice that the entity object, the runtime object, is instantiated at login time and deleted when log out. A database is persistent and it stays there forever, for years. So entity object pulls data from the database at startup and saves data to the database at the end of the session. But it's transient. But the information it contains should be long-lived and persistent. The dynamic object in the analysis model. So encapsulates and isolates changes to the information it represents. So examine the use case model to determine what domain model classes are accessed to carry out the use case. So basically, you have a collection of domain model classes. So to design the entity classes, you look at one use case to see which domain model classes it needs, and then write one entity class for each domain model class. Yes.
Do you mean that all the entity class names should be consistent with that in the database? For example, if the for example, select course manager should interact with the database for course and course offering, so we should illustrate two separate entity class, say the course entity class and course offering entity class.
Yes, of course.
So one entity class should be correspondent to one database entity.
Yes. Yes. Domain model, you pick a subset of the domain model classes as your entity class for a use case, right? Because a use case may not use all of the domain model classes. And you should use the same name as the domain model classes because they represent the same information, right? So here's the use case, and you look at, so you identify the three entity classes from the use case flow of events. So you see step by step which database item it needs, and decide, okay, it needs a course offering, and professor. Then you draw three entity classes that correspond to the domain model classes one-to-one. Control class is this manages coordination, doesn't have a correspondence in the application domain, unlike the entity classes. It's a glue that ties together other classes. Represents control and business logic. Again, encapsulation and isolation. So the strategy is to initially assign one control object or class for each actor use case pair that's responsible for the flow of events in the use case. So similar to the boundary classes. And if you have complicated behavior, you may need several control objects, or you can merge several into one if they're very simple. So we can handle this later. So control object should be tied to at most one actor. So by doing this, we isolate changes required to only the functionality needed by that actor. Sometimes if the control is simple, or if the UI is very complex, and you put a lot of logic in the UI, then perhaps you can eliminate the dedicated control class and use the UI also for control. So instead of a 3-tier architecture, boundary control entity, you can have a boundary entity, a 2-tier architecture, if the control is simple. So by 3-tier, I mean this, right? Professor is 1 to the at the UI end, and these are at the database end. Of course, these are not the database. There's another database sitting somewhere, and they can pull information and save information to the database. And then this is this middle layer. So sometimes you can remove this one if the logic is very simple, and put other logic inside of the I'm sorry. So there should be a control here. By 3-tier, I mean 1, 2, 3, and you can put the control logic in the UI class. The actor is outside of the system, so actor is the human. So here's the use case. Here's the analysis classes. And then this is one actor use case pair. So you have one. Convention is to have MGR, manager, at the end of the name, meaning that it manages interactions among other objects. And then how do you connect those? So let me see. I think I skipped some slides. So the connection is typically from control to entity, and from boundary to control. So sometimes you can have a boundary to entity directly. That's fine. You can even skip, delete the control altogether. But from an entity class, you should never originate any connections. That is, you cannot do this, for example, or do this. So entity classes are sinks, right? They can only receive invocations. They should not initiate any invocations. So that's to nothing prevents you from doing that in your implementation. You can write bad code, but it's good design practice to have entity classes as the passive things that wait for invocation from other classes. And the UI, of course, should be initiator of things. When you click a button, it initiates interactions to control or to entity. So interaction diagrams, we discussed sequence diagrams. Right, best practices. Boundary should not interact with boundary, and entity should not interact with entity. Control can interact with any boundary entity and other control objects if necessary. So actors can only interact with boundary objects. Obviously, that's why boundary objects are designed, is to encapsulate the system so the actors can only see the boundary objects, not insight directly into the entity. Yeah.
In a single actor and use case pair, will there be cases that will have two boundary classes? In a pair of actor and use case, a single pair. It seems that there's always only one single boundary class called Barbara UI.
Yeah. As we discussed, initially you always assign one boundary class for each actor use case pair, but later you can refine it into multiple ones if you find it necessary. If the UI is very complex, we had an example for the professor UI. You can right. So, or you can aggregate multiple boundary classes into one if they're simple. So it's all design decision. For our projects and perhaps for the exam, you always design one boundary class for each use case pair. That's enough. So sequence diagrams, you have the lifelines. So relative time and messages, and combined fragment. This is where you can express loops and other conditional behavior. So here it says loop. And here's a guard condition. Course exists. While course exists, update the course. So you see this classical interaction pattern where actor talks to the UI, UI talks to the control talks to the entity. So then you may have return. Return meaning that if you make a method call to the other object, say course dot get data, and that guy will return a value. That's the return arrow. So you can have activation time representing when this particular object is active. So for it's shaded, meaning that the thread of control is here. When it's open, it means that it's waiting for a response from another object. So it's essentially makes a call, and that guy is taking a long time, and this guy is waiting. Perhaps it's going through a network. So combined fragment groups sets of messages together to show conditional control flow. So here we see the alternative. If you try to, if the balance is greater than equal to amount, you can do the debit transaction, do the check. Else, you check is bounced. So this is the out keyword for the combined fragment, indicating if then else. So break means that if the guard here is true, balance less than amount, then you go into the break fragment, and when you are done, you exit. You jump out of the sequence diagram. So it's like an exception handler. And all the others are skipped. The rest of the sequence diagram is skipped. Of course, if the guard is false, then you skip. You do not execute the break fragment, and you execute the rest of the sequence diagram. So loop. So you have a fragment with a guard. While the guard is true, you execute the fragment repeatedly until it becomes false, and then you exit. If the guard is absent, then it's true, and then you should specify a repetition count. Well, based on the repetition count, that is, if you're trying to say for each seminar get mark, and then you finish when you have gotten the mark for every seminar. So opt means that. So if the guard is true, you execute the opt, this part. Otherwise, you skip the opt. So it's equivalent to a single guard out alternative with a true branch but not a false branch. So notice there's also a difference from break, right? If it's a break, if the guard is true, you execute the break fragment, then you exit. You skip the rest of the sequence diagram. But here, you execute the rest of the sequence diagram anyway, whether it's true or false. So par means that it's parallel. So if you use a microwave, you know that it's heating the food while it's rotating the food. These two are occurring simultaneously. Therefore, you have par to represent concurrency. So you may have creation of objects. So you have new pointing to an object, indicating creation. Destruction is this cross. So the arrow, if it's this shape, the solid arrow is synchronous, and open arrow is asynchronous. So this means that synchronous message means that you send a message, then you sit there waiting for a reply back. Sender loses control while the receiver before the receiver returns the reply back. But asynchronous means that you send a message, then you forget about it. You move on with your own business. And then later, perhaps you get a message back. You have to handle that. So if it's synchronous, then you always have a return. You can skip it. You can omit it for clarity. If it's asynchronous, you may or may not have a return. So also you can have self message. You send a message to yourself. So kill checkers, and then so self delegation. So interactions should be visible and reviewable. So there's no single right answer. As you do your project, you may find that it's very very difficult because there's no standard answer. And also it's hard to grade for me also because I don't have a standard answer to compare to. I have to look at each one and really understand each one. So use case partitioning, each use case is divided up into a collaboration of boundary, entity, and control to localize local changes to have a stable system. Make judgments as to where to place the functionality. So entity classes are easy. They just store information, perhaps with a simple get set methods. But boundary and control can be a little fuzzy. Sometimes you can place the functionality into boundary. Sometimes you can place it into control. So here's a use case. Here's the analysis model. This guy, dotted oval, means that it's use case realization dash analysis. It represents a realization of a use case in the analysis model, consisting of all the analysis classes that participate in the use case. So you may have you should have a trace relationship between them. So you should have traceability, meaning that you should for any analysis class, you should point to it and say which use case it is for. So that's why UML unified process is use case driven. Use case is in the middle, if you remember, and you have other views, 4+1 view. So state machine describe the behavior inside an object. So what the object does when it receives a message. So last time you asked what's the difference between the object's behavior and its interface. So the interface is a collection of operations, and the behavior is the state machine. How the object behaves when it receives an object, receives a message, perhaps by invoking the operations in the interface. So here's the state machine example. Initial state and final state. So this guy is the initial state, but it has a transition into in-credit state without any guard or event triggers. Therefore, when an object is created, it goes in the initial state and then immediately goes into an in-credit state. So sometimes we say in-credit is the initial state. But to be very precise, you should say the black dot is the initial state, but it just doesn't stay there. It just goes into in-credit immediately. So, and you have events and actions. So say if you're in credit, you get a closed account event, then you do this action. Set state equals inactive. State should be an attribute in the class, and go to closed state. And then after 5 years, this is another event. You should go to the final state. It means that the object is destructed. So what happens if you get a closed account event in the say frozen state? Because there's no outgoing transition from the frozen state with the closed account event, it ignores the event. The event is lost. So only when you have a outgoing transition, then you handle the event. Otherwise, you ignore it. So state has a duration. You can stay in it for many years. Can be characterized by the value of one or more attributes, like the account. If it's greater than or less than 0, it can be in credit or withdrawn, or existence of a link. Say a professor may be teaching or not, depending on the existence of a link to a section object. If it has a section link, then it's teaching. He's teaching. Otherwise, he's not teaching. So you can discover these from sequence diagrams. So initial state and final state. States may be named or anonymous. If some state is transient and not important, you can leave it anonymous. Transition takes 0 time and cannot be interrupted. So nothing takes 0 time. It always takes time. By take 0 time, we mean that it's atomic. So when it's doing some action, it must finish all the action and go to the next state before anything else can happen. If some event arrives during the transition, then it's buffered until the transition finishes. Then it's handled. So event trigger. So transition may be triggered by event with a guard condition, which is using square brackets. and effect list. That's the invocation of some operations, or you can write arbitrary code in the effect list. So you don't have to invoke only the interface operations. You can do anything, including manipulating the private attributes, because this is the internal implementation of a class. You don't have to respect the interface. So event is instantaneous in time. So you have four events. So call event is a synchronous call from another object. Signal event is asynchronous communication. So in the sequence diagram, remember, if it's a synchronous call, it's a solid arrow. Right? If it's an asynchronous, it's an open arrow. So when you design your state machine, you can look at the sequence diagram. If the arrow pointing into this object is a solid arrow, it's a call event. Otherwise, if it's open arrow, it's a signal event. Change event is a Boolean condition becoming true. So notice the difference between the change event and the guard. A guard is specified with a square bracket. After an event, you have a guard. So it means that when the event happens, if the guard is true, then you take the transition. Otherwise, you ignore the event. You don't take the transition. So, but here you have the round bracket for the change event. It means that it's an active thing. When the balance is less than 0, this particular event is triggered when balance less than 0. Think of it kind of like an active database. When the balance drops below 0, the database sends something out. So while the guard is passive, it must be paired with another event. So many times you can use both styles, either style, to specify the same thing, but they mean different things. See here, you have these events. Alright, there's also time event after a time duration. So when balance less than or greater than or equal to 0, you make some transitions. So these are triggered by the balance change. So, and also these are so-called self-transitions. That is, when the deposit money event is received, it invokes add money, but doesn't transition to any other state. So it's an internal transition. Yeah.
One thing I'm not clear about is what's the relationship between in credit state deposit and add money, or withdraw and the sub.
Oh, deposit is the event. Add money is the effect list. Is the action you take.
If the event is triggered, then we take the corresponding.
Take the add money action. So this is the so-called effect list, right? Effect list, atomic procedural expression executed if and when the transition fires. Of course, here it's a self-transition, so you don't go to another state, but you just invoke add money if the deposit event arrives. Just to make it more clear, you can write this in a different way. So this is the change event. If you write a guard-based style, perhaps you can write, say, incredit as part of the withdrawal method. You can say withdrawal with a guard if it's greater than if it's enough. There's enough money. You subtract money and stay in the incredit stage. If there's not enough money, then perhaps you with a guard balance less than 0, you go to overdrawn. So just another style of specification.
You mean that add money can be also written as a self-cycle, because it's a transition back to himself.
Yes, there's a subtle difference between these two. If you have a self transition as an arrow, then you invoke the entry and exit actions. If it's written inside, you do not invoke the entry-exit actions. For this case, there's no entry-exit actions, so there's no difference. But sometimes there's a difference. We didn't discuss this point in detail because it's too much in detail.
It won't be tested.
Right, exactly. I think we have entry-exit somewhere. Let me look for action. Do we have entry-exit? No? No, we didn't discuss entry-exit action, so forget it. Entry action is something you execute when you enter the state. Exit action is something you execute when you exit the state. But we didn't have it in the slides. So events are processed one at a time. If the event doesn't trigger any transition, it's ignored. That is, if the current state does not have an outgoing transition with the event as the trigger, then just drop it, ignore it. So it should be deterministic. That is, whenever something event happens, you should have only one choice as to which transition to take. If you have multiple choices, then it's probably an error. It's non-deterministic. So you may have two ways of transitioning. Non-automatic is the one we have seen so far. It's caused by an event. If it's automatic, means that transition without labels fire immediately when the state exits, when the state activity completes. So for the example before, from the initial black dot to the initial to the other state, that's an automatic transition. There's no label on the transition, so it's taken immediately. If there's an event label, you must wait for the event. So actions and activities. Action, processing for transitions between states and entry-exit of a state. Activity happens while the state is active, and it takes time and can be interrupted. Well, actions are atomic. So in a state, all right, entry exit is here. So you can have entry action, exit action. So do activity means that you're doing this particular activity continuously while you are in the state. It can be very time consuming, and when you're done, there's an automatic transition, you should get out of this state. So this is the outgoing transitions, and no behavior means that. You are waiting for an event. If no event happens, nothing happens. But if you have a do specification, it means that you're doing something while you're waiting for the event. Or in the case there's no event, no waiting for event, then you finish the activity and take the automatic transition. So here's the example. When there's a do here. So when it goes into canceled, before you destruct the object, go into the final state, you do a bunch of things to clean up the database. So unregister all the students, delete a schedule, delete self. So when they're done, this is transition is automatic. This guy is automatic transition because there's no labels on it. Then you go into the final state. So closed. Notice while you're in the closed, you can handle two events. Drop student and registration closed. While you're in the open stage, you can handle how many events? You can handle 3 events: add student, drop student, and registration closed. Depending on the guard, you go into different next stage when the registration closed event happens. So if you receive the registration closed, you transition to another state. But if you receive add student, drop student, you stay within the open state, but do some action and stay in the state. So while if you're in the closed state, you get an add student event, what happens? Nothing happens. It's ignored because there's no outgoing transition for that event in a closed state. So there will be a question for state machine design in the exam. So will be a question. So here's another example. So you can compose states into a composite state. Name it unavailable. So we have.
The problem is why the state machine is so simple that it did not include many operations bound to the entity name, state name. Should we always include the operation name?
Oh, you mean for this guy it's too simple? I mean you don't have the slash action.
In a single state there were a bunch of things, but it didn't have.
Oh, right. For this guy, there's a reason because there's whenever this event is received, it goes into another state. Only when you get an event, you do something and you stay in the same state, then you write something inside, right? So if in this particular case, there happens to be no such transitions, self-transitions. There happens to every event you get drives you to another state. Well, in the previous one, when this add student happens, you stay in the open state, right? So for example, for closed, there's nothing inside because drop student and registration closed drive it to open or offered, right?
How about the in credit one example? There are 2 examples. One is just simple as stay with in credit with overdoing it. But another one. Yeah.
There's another.
7 slides later, there's a complete version. There's a single version.
This is the simple version.
And you may see there's this one. This one.
The left.
This guy?
Yeah. I think they're the same example, right? So.
Oh, okay. Let me see. Deposit withdrawn in credit when overdrawn. Oh, right. So this one is omitted the withdrawal and deposit events. So it's incomplete. Yeah. So yeah, you should have these events. So state machine. This is the composite state machine. So this guy, this little icon here, means that you have another state machine inside of it. So you have superstate and substate. So I think these arrows are wrong. So essentially, each one of these are 3 substates, and this whole thing forward is the superstate. These arrows are pointing to the wrong direction, wrong place. So anyway, so any transition into a composite state gets translated into a transition into the initial state in the substate state machine. So the transition into the forward state, select F, goes into the first. And transition out of the composite state gets mapped into many transitions, each one coming from each of the substates. So select N is coming out of the forward state, and you get mapped into 3 transitions out of first, second, and third. So that's a different behavior. You map it onto a flat state machine. So concurrency happens. Say you take a class, you do 3 things at the same time. You do labs, you do project, you do exam, and so when all things are done, you can go to the past, so or fail. So this is concurrent as opposed to sequential in the previous change gear example. This is indicated by the dotted lines indicating swim lanes. So you can have synchronization bars, fork and join. So notice that this particular fork and join is identical. If you didn't use the fork and join synchronization bars, you just had an initial state here and a final state here. Initial, final. And delete these bars. You go to the border of the composite state. So they mean the same thing. Both mean that it's both must complete before the next cleanup state can be entered. But for this one, it means different. It means that when either A2 or B2 finishes, you go to cleanup, not both. So it's a wrong. This is a wrong specification for the problem. So now we discuss concurrency among state machine diagrams. So we discussed parallel states, that's concurrency within the state machine. But with different state machines, they can talk to each other as well. So here's one example of 2 state machines, ignition and transmission. Ignition has a guard that depends on the state of the transmission. transmission is in neutral, then when you turn key, you can go from off to starting in the ignition state. Otherwise, if you turn key, nothing happens. That's one form of communication. Another form is sending events. So when you your remote control, you press the power, and you can say VCR.toggle power. It means that this little thing here means that it's an outgoing sent, outgoing message. VCR is the other class name. Dot is the event name in the other state machine. So it means that send the outgoing message to the VCR object with the toggle power message, toggle power event. So and then VCR gets it and makes a transition. So you can think of these two as, one is for this guy, it's a shared memory communication. They both can see each other's state directly. For this guy, you can view it as message passing communication, where you cannot see inside the other object's state machine. You can only send and receive messages back and forth. So it's not necessary to produce a state machine diagram for every class, only for classes with significant dynamic behavior. So sequence diagrams can be used to discover these objects, those that send and receive many messages. Perhaps you should have a separate state machine for it. If an object only sends and receives a few messages, then it's not necessary. So the activity diagram describes a flow of control. So here's an example of order processing. So you receive order, you fork off these things, two branches, authorize payment and check item. So you have iterative, means that you do these things iteratively until you run out of the line items. And you have fork and join as well. So notice that this guy is for the overall business flow, which may involve many objects, while state machine is only for a single object. So you may accept, and wait. So this is a classic wait icon. You may have exceptions. So here's the signal example. You send itinerary and you wait for reply, itinerary confirmed. Or you wait for 48 hours. And whenever either one happens first, you go into the next stage. Book itinerary or cancel itinerary, and then you go to finish. So partition shows who and what is responsible for an activity. So control flows across partition boundaries. So for this example, you partition it into a finance department and order processing department. Manage the section. You may have 3 partitions: register, professor, and student. So so this is decision node. If it's offered, you go to assign grids. If it's cancel, you go to cancel section. So this thing looks like a state machine, right? But it spans multiple objects.
It's not always the case that we can always find a partition.
You can always, yes, you can.
Oh, it's up to design.
Yeah, sometimes you don't draw the partition, but it's always possible to do the partition. So sometimes you just omit the partition. So notice that you can also use activity diagram for another purpose, to describe the inside of a procedure. So this is a check register for a course procedure. You check enrollment, and if it's check exclusions, check permission, and final register or board registration. So this is the internal behavior of the register for a course operation. Think of it as the you can map it into a flow graph. Later we used in the unit testing, if you recall. So you can group sequential nodes together into a single node and get a flow graph from it, and then you can do the cyclomatic complexity and designing the independent path set, etc. So activity diagrams can be used at two levels of abstraction. This is a fine-grained abstraction where you're describing the internal details of a course register for a course procedure, or you can use it at a high level to describe the overall business flow, as in the previous order processing example that spans multiple objects. So this is for a single procedure inside of a single object. So yeah, to show the procedure flow of control of an operation, or to show workflows and multi-threaded programs. One is a fine-grained, one is a high-level coarse-grained. So package, analysis package, cohesion and coupling, we saw this many times. So it does one thing when it's cohesive, low coupling when it has minimal dependencies with other packages. We saw cohesion coupling for module design and also for design subsystem design at the design in the design model. So 7 plus 2 plus minus 2 heuristic means that it should talk to 5 to 9 other things. Shouldn't talk to too many other packages. So package design have many. You can have choices. So for you can have information maintenance as a package, course registration as a package, and registration data as another package. And this is application-specific layer, meaning that they contain classes that's specific to the course registration application. But this is application general layer, meaning that it can be used for other applications, like for billing application, for example. They may have more fine-grained partitioning to divide the information maintenance into two, course maintenance and people maintenance. Or you can add a separate UI package that gathers all the UI boundary classes. Or you can partition the data packages into two, people data and course data. Then you can have more fine-grained dependencies. So people maintenance only talks to people data. Course maintenance only talks to course data. Course registration needs both data. So in the notes, you have this how the analysis classes are grouped into these packages. So that's the retrospective. Analysis model localized changes. So use case realization, dash analysis, localized changes in use cases, and everything localized changes. So design. So you choose a subset of design goals because you cannot hope to realize all goals. Prioritize the design goals. Consider the technical and management constraints. Hardware, software, programming languages, existing software, development people, organizations. These are considered in the design stage. They should be ignored in the analysis stage. So we discussed architecture style design patterns as well as frameworks. So architecture style and design pattern is a solution to a problem described in literary form, while the framework is a reusable chunk of architecture. So framework is software. Say Microsoft Foundation classes is a framework for developing UI applications. But architecture style and design patterns are text. So you read it, you understand it, and then you write code. So architecture style, we discussed, say, multi-layer, UI layer, application, a middle layer, and bottom layer, model view controller. So yeah, I think in the notes you have more layers, more examples of architecture styles. Design pattern. So we discussed facade, where this is a French word, facade. So you place a single class at the entrance. Everyone else can only see this single facade class, not the other classes. So this is really a generalization of the interface concept, except interface is for a single class, or facade is for a subsystem. Proxy is when you use this proxy to represent a concrete object to save time. So when you load the document, you only load the proxy, which is very easy, very fast to load. And when you actually look at the image, then you load the actual image from disk. So now you need to take each of the analysis classes and turn it into design classes. So boundary class implementation means that you need to choose the UI technology. Entity class, you need to choose the database management technology, relational database or object-oriented database. Control class, you need to decide distribution, performance, and transactions. So how many processors, how many computers do you need, and how to distribute each one. So all these should be considered at the design stage. So high cohesion, low coupling, again. So here's one example where you optimize for performance by adding attributes. Okay, you add a status attribute to the rental copy class, so that you can save time when you look up the status. You don't have to traverse the links to determine the status. You can just look at the attribute. But the cost is, of course, you do more work when you actually update the links. You update the attribute, a status attribute. So subsystem looks like a package, except it has this little shape here, meaning that it is a subsystem in the design model. Cohesion and coupling. So layers and partitions. This is also very similar to the analysis model's package concept. So layers are vertical, partitions are horizontal. So this is 3 partitions and 4 layers. So here, this is the analysis package diagram we saw before. Now in the design, we have the subsystems corresponding to the packages, but we have 2 new ones: system security, generate report. So these 2 are added in the design stage. You can add more subsystems, but at least you should have 1 subsystem for each analysis package. So they can have interface for the subsystem. So this guy has an interface. Now I can use the facade pattern to turn it into a single interface to minimize coupling. So deployment describes how the functionality is physically distributed to processing nodes. So you need to consider the computing capacities, etc. So this is the this shape here, like a box, meaning that it is a physical location, physical computer. So you need to so this is the web server box. You need to place the subsystems inside of this box to show that these are executing on the web server. This is the subsystem running on the Durham computer. So design model. Yeah, so we'll discuss testing. I think we'll continue next class. We'll also do some TRS questions. So difference between validation and verification. Validation means that you built the right product. Means that if it fulfills all the user's requirements with acceptance testing. So in your demo on the December 10th, we'll do validation. So verification means that you have built the product right. So that is, you're checking to see there's no bugs. You can have a perfect bug-free system that doesn't fulfill your user's requirements. So then it has passed verification but didn't pass validation. You can have a system that fulfills all the requirements but it's full of bugs. Then it has passed validation but didn't pass verification. So all the other testing deals with verification, but only acceptance testing deals with validation. So you cannot show the absence of errors. You can only show software errors are present, because you cannot exhaustively test any realistic software. Testing is a destructive activity. So this simple example, it takes 3,000 years to test it because of the exponential increase. So it's 5 to the 20th power number of possible combinations. So a test plan includes a testing strategy, resources, and a schedule. So testing has 2 types: white box, black box. White box is when you verify component logic, we have source code. Black box is when you test the binary. White box tests are tested in the small because it's usually used for unit testing. and for small-scale module testing. Black box tests are used for system-level testing and testing larger subsystems. Regression tests are selective white box and black box retesting to ensure that the old functionality still works. So independent paths testing and logical decision, condition testing, loop testing, and data flow testing. These are 4 white box testing techniques we discussed. So we discussed why we need to cover different paths, not just different statements. So for this guy, if you take this right branch, it's fine, but if you take the left branch, there's a divide by 0 error, because I is 0 and x equals y divided by I. Therefore, if you take the right branch, you have covered 4 statements. But that's not enough. You need to cover both branches as well. So basis path testing, you draw the flow graph from the activity diagram, or you can draw the flow graph directly. Determine the cyclomatic complexity, which is the upper bound of the basis set, number of basis paths in the basis set, independent paths in the basis set. Then prepare test cases to force the execution of each pass. So flow graph, each circle represents one or more non-branching source code statements. So it's a more coarse-grained representation of the activity diagram. So each of the little circle here may represent perhaps hundreds of statements. So it only shows the skeleton of if then else and while and other control flow information. Ignores all the sequential code. So for this guy, you can draw the activity diagram like this, and then you can draw the flow chart, flow graph, which is abstraction by grouping linear non-branching statements together to get the flow graph here. Or you can draw it directly. So cyclomatic complexity, the most common way of determining it is to count the number of regions. And all the other 2 ways get the same result. Number of edges minus number of nodes plus 2, etc. And then you determine a basis set. So for this example, you have 1, 2, 3, 4. Cyclomatic complexity is 4 because there are 4 regions. 1, 2, 3, and 4 is the one outside. So independent path is any path that introduces at least one new set of processing statements or a new condition. So basis set is a set of independent paths. Cyclomatic complexity provides the upper bound on the number of independent paths. Could be equal or could be just the upper bound. So here's the independent paths. You have 1, 2, 3, 4, right? So cyclomatic complexity is also 4. Right, 1, 2, 3, 4. 4 regions. So they're equal for this case.
You said it's upper bound, so is it possible that less than 4?
Yes, we have an example where it's less than. I think it's this example. So here you have 2 independent paths. 1, 2. But the cyclomatic complexity is 3. So
Just traverse all the edge.
notice that you can have different basis sets. 1, 2, 4, 5, 7, and 1, 3, 4, 6, 7. That's the one I drew. Or you can have 1, 2, 4, 6, 7, and 1, 3, 4, 5, 7. So either one is okay, but they all have true paths. So even in path, a path that introduces at least one new set of processing statements or new condition. So if you notice, if you draw the left and right, then any other path doesn't introduce any new statements or new conditions. So that's only true. Where is it? Hold on. So notice that compound conditions get turned into multiple control nodes. So here you have one statement: if status is available or status is rented or something. So it gets turned into 3 decision nodes. Number of decision nodes is dependent on the number of simple conditions. So it's not true that each statement gets turned into one node. One if condition can be turned into multiple nodes if it's compound. So so here you have basic set is this is 1, 1, 2. This is 1, 1, 2, 3, 5, 6. This is 1, 1, 2. No, this is 4. Because you have decision nodes, and you need to traverse both branches of the decision. So any node with 2 outgoing transitions is a decision node. So you have this is a decision, this is a decision, this is a decision. So perhaps with the 1, 4, 6, 1, 2, 3, 4, 6, and 1, 2, 3, 5, 6, you have covered all the statements. But there's a decision not covered. That is, 3 to 5. Yeah, so you need to remember any basis path is an independent path is a path that introduces at least one new statement or new condition. So in here, 1, 2, 3, 5, 6 doesn't introduce any new statements, but introduces a new condition. So it's also an independent path. Okay, we'll continue next time.